When integrating using double integrals, your bounds are not always going to be constants. So previously, what I'm assuming before you guys learned this is maybe you would have some rectangle that you would integrate upon. And this is our rectangle. And in the shaded region, you would have lines that just boxed up a rectangle and all your bounds were constants. Well, your bounds can be non-constants. And what I mean by that is your bounds can be a function of something, like a quadratic. Your y bounds could be this quadratic, and your x bounds could be some point in the quadratic and 0. And now your shaded region is something that doesn't look even close to a rectangle. Now, how would you solve for these integrals? Well, you can solve for these integrals using functions as your boundaries. So, what do I mean by this? Well, let's start with some problems. We're going to integrate the region x squared plus y squared along an area. I'm going to draw out our box now. And the region we're going to integrate upon is defined by the x boundaries of x equals 0, x equals 1, and y equals 0, and y is equal to x. And our shaded region looks something like this. Now, how would you start off doing this problem? Well, if you look at an integral, you would need to set this up like so, and you would need to choose some order in which you would integrate upon. And the order of integration matters, but for this problem it won't matter so much. So for dy, we're going to choose, let's integrate with respect to dy first. And when you integrate with respect to dy, you have to keep in mind that the top bound of this dy integral is the top boundary. So b is the top boundary, some function that represents the top boundary of your region, and a is some function that represents the bottom boundary of your region. So the top boundary here would be of this region, what bounds the top of this region is just y is equal to x, and what bounds the bottom, y is equal to 0. Therefore, our bottom boundary is 0 with respect to y, and our top boundary is represented by the function x with respect to y. So just whatever y is equal to at this time. And how about our x boundary? Well, our x boundary, b, represents the right side, and a represents the left side. So the right boundary of this region is x equals to 1, and the left boundary is x equals to 0. Therefore, a is equal to 0, and b is equal to 1. And we have our integral set up now. Now all I have to do is solve for it. So I'm going to integrate with respect to y first. So I'm going to take out the x integral for now. And we're just going to integrate with respect to y. And the integral of this with respect to y is x squared plus y squared. Oh, no. xy plus y to the power of 3 over 3 from 0 equals y and x is equal to y. And if you plug everything in, what you get is, let's move this graph because it's blocking the way a little bit. If you plug everything, what you get is x to the power of 3 plus x to the power of 3 over 3. So all I did was substitute x into y here. And then now we can integrate with respect to x. So the integral with respect to x has the boundaries of 0 and 1, and then we just have to integrate our previous answer with respect to x. And the integral of this with respect to x is x to the power 4 over 4 plus x to the power 4 over 12 with from 1 to 0 is equal to x. And then when you plug in 1 and you plug in 0, you get 1 over 4 plus 1 over 12, which is equal to 1 over 3. So the integral of 1 over 3, the double integral, sorry, of this region, shaded blue, is 1 over 3. The next problem, our integral will be along the region R. Our function will be x, and you're integrating upon an area. Hold on, I need to change these, man. These are pissing me off. PMO. Okay. And our boundary looks something like this. So the y boundary will be, let's draw something better. Y. Y is equal to square root of x. Our bottom y bound will be y is equal to 0. And our x bounds will be x equal to 0 and x equal to 4. So for this region here, you can decide whether or not you want to integrate with respect to y or with respect to x first. For this, I'm going to integrate with respect to y first. Just because we already have the top boundary function with respect to y, which means y is isolated here. So the top bound of this function is square root of x. So our top bound is square root of x, and the bottom bound is just 0 for y. Y is equal to 0. Our left boundary is 0 for x, and our right boundary is 4 for x. So this is our integral over here. With respect to y first, and then with respect to x. First, let's integrate with respect to y. dy. And since x is just treated as a constant inside of this integral, our integral turns out to be xy, 0, square root of x is equal to y is equal to y. We can plug in square root of x here. And you get x times the square root of x. And if you plug in 0 into y as well, you just get 0. So we'll ignore that. X square root of x is also x to the power of 3 over 2. So now this is our function. All we have to do is integrate with respect to x now. And this is just a simple calculus 1 problem. So the integral of x over 3, 2 is 2 over 5, 5 over 2 from 0 to 4. 4x. For equal to x. If we plug in 4 and 0 into here, we get, what is a square root to the power of 4? Yeah, this is a big number. Just plug this into your calculator. But these problems are just the same thing as what you would normally do with constants. So, just a quick review. If you have a double integral with some function xy, dA, let's do dy dx. So we're integrating with respect to x first. Our b here is the top bound, and our a is the bottom boundary when you're integrating with respect to x, and when you're integrating with respect to, when you're integrating with respect to y. Now we're integrating with respect to x. So our d value here is the right boundary function, and our c value is the left boundary function. And just like how you would substitute integers into your integrals, you just have to substitute the function whenever you're plugging things in. So if you have any questions, put it in the comment section.